Okay, so in today's session, we are going to cover a few numerical questions based on week three. Okay, so before going on the questions, let me just briefly discuss what is there in week three. So in the last week, we have discussed about the stability, BIBO stability. Okay, so in this week, we'll see what happens when there is a zero, right? Zero in the left hand plane, what is its effect, and if it is in the right hand plane, what is its effect, right? Okay. Okay. So let me briefly discuss through notes. So I think now you're able to see my screen. Okay. So in the last week, we discussed about the stability. Okay. So what do you mean by stability? We have the transfer function. So how do we derive the transfer function? So we are given the equation. Okay, it takes normally a ODE. Okay, differential equation. So by keeping the initial condition equal to zero, okay, we just take the Laplace transform and find the output to input. So that's called as the transfer function. Okay, so this is the transfer function which is output to input. Okay, so the input can be anything. So we don't denote this as PS. So PS is the, you can say it's a plant transfer function, right? So this is the transfer function with initial condition, okay, equal to zero. So this is how we drive the transfer function. So what we have seen in the week two is if we place US equal to zero and find out its roots. So its roots are called poles of the transfer function. Okay, and by finding the poles of the transfer function, you can determine whether the system is stable or not, right? So if its poles are lying in left hand plane, okay, so this is the complex plane, okay, this is the imaginary axis and this is the real axis, okay, so this is left hand side plane, okay, okay, so this is left half plane, okay. So if your zeros are lying in this plane, okay, in this side, so we say our system is stable, okay. If any of the pole lies on the right hand side, then we say our system is not stable, right? And if it is lying on the imaginary axis, we will say it's a marginally stable, and the poles lying on the imaginary axis should not be repeated poles, right? Then again we'll say our system is unstable. So that we have seen in the week two. So in this, we'll see. So what is the effect of zero, right? So we have seen here. So yeah. Okay. So the effect of zero. So through examples, we are seeing what are its effect. So first we will see, like, if we have zero, like in this example, okay, you see there is a zero here. So what does it do? Okay. So first concept we studied is about the dominant pole. Okay. So if you see in this example, we have two poles, right? So S equal to -1 and is S equal to -10. So how do we decide which is dominant, right? So which is decide, how do we decide? We see the performance, okay, its output y of t, and we'll see that S equal to -1 is the dominant root, right? Because its effect is more. Okay, how you can see the effect? By drawing the y of t versus time, right? So you can see the -1 pole has more effect on the output. That's why we are saying it is a dominant pole, right? And you can say it's near to the origin. That's why. Okay. So indirectly, you can say the pole which is nearer to the origin, it is the dominant pole, right? So in the second example, we have seen, okay, in this example, what is its effect if we add 1 0 to it, right? So we have added a 0 at s equal to -2, which is nearer to -1, right? So what does it do? So again, you see y of t, right? So this, so what it does is, again, it alters the steady state value. So this is the steady state value. See, initially it was 1 by 10, now it is 1 by 5. But what are its effect? Major effect is, okay, it reduces the dominance of -1. Okay, so if you see these coefficients here, so it's these coefficients. Okay, so let me again, if you see, compare these values here, 1 by 9 and -8 by 10. Okay, so these are the coefficients. So if you see -1 by 9, okay, it's a larger value as compared to 1 by 90, right? So we are comparing. So okay, we are comparing with respect to this, right? Sorry, with respect to this one. Yeah, 1 by 9 and 8 by 90. Sorry. So let me erase. Okay. So we are seeing this coefficient, right? With respect to 8 by 90, right? Here also. Okay. We're just comparing two coefficients and we find out that if we add a 0, which is nearer to the dominant pole, what its effect will decrease, right? So you can see in the this y of t waveform also. Okay. So that it, what it does, it affects the performance of the system, right? So stability you have already studied. Now we are dealing with the performance, right? So we have seen that. So again, what we do, if we add this 0 very closer to -1, or directly we'll say, okay, let us put a 0 at s equal to -1. So the system will behave as a, because there will be a pole zero cancellation. Okay. So we'll say that a second order system will behave like a first order system. Okay. So initially you can see it was a second order system. Okay. So s plus 1 into s plus 10. Okay. So the plant transfer function is supposed to be second order system, but due to this pole zero cancellation, if you see what is remaining here in the transfer function, 1 by s plus 10, only a single pole. So it behaves like a first order system. Okay. So again, this is the effect of pole zero cancellation. Okay. Again, the major effect, what will be happening to the system if we add a 0? Okay. So the 0 is lying in the right half plane, right? So s equal to 2. So earlier the case was s equal to plus 2, right? If you see this, s equal to plus 2, but now see here, now the 0 is at s equal to 2, right? So it is lying in this part, right? So for the poles, we say, directly say the system is unstable. So what is its effect? Okay. So again, to measure its effect, we have to see its output, right? So the output is here. So, okay. So this is the output, and if you plot with respect to time, you'll get the waveform like this. Okay. You can see this is the steady state, right? The system want to achieve this steady state, but what is happening due to this 0? So initially, okay, so initially what is happening? The system is moving opposite. Okay, so this is its effect, right? If you see, able to see this green one, I am just marking on the red one. Okay, so its effect is this. Due to the right hand 0, due to the 0 which is present in the right hand side, the system is going opposite initially. Okay, for a very small duration. Okay, so this is the effect, right? Because of that. Okay, that we have seen here. So again, what we call this system, if we have 0 in the RHP, that is right hand plane, it is called as non-minimum phase 0. Okay, a non-minimum phase system also. For a particular system, that PS, this PS is called non-minimum phase system. Okay. So again, we have seen what happens if we introduce time delay. Okay. So let me change to, okay. Okay. So here you can see we have introduced a time delay in our input. Okay. TD is the time delay, right? So again, you'll get the expression like this. Okay. So we'll be using some approximations here. So the important one is here, Faraday's first order approximation, right? So this is very important. Whenever if you get any delay in the input, you have to use the Paredes first order approximation. Okay, so basically just replace E minus TDS, so this term with whatever this term. Okay, so this is Paredes first order approximation. Okay, so again, if you do this, what will happen to the transfer function? You see, again there is a 0, okay, in right hand plane. Okay, so what does it do? Again, it introduces your y of t will be in the opposite direction initially. Okay, so this is its effect, right, because of this approximation. Okay, so just remember that. So again, we studied about the, so in week 1 and week 2 mostly we studied about the system, right? So type of system on all this. Now we are just considering the closed loop system. Okay, CISO LTI causal dynamic system that we have studied. So we are closing the loop here. So, and we are trying to find out the closed loop transfer function. Okay, so initially we were working with the open loop transfer function. So only system was there. Okay, now we are closing it with the sensor, controller, and actuator. Okay, so this is the simplified. So if you see any reference book, you will see this. Okay, okay, and in the reference book you see GS will be equal to CS into PS. Okay, so CS is the controller transfer function and PS is the plant transfer function. So this is actually the forward loop transfer function. Okay, forward path gain. So what? So already that is mentioned in the week 2 lectures here. Okay, so this is the transfer function you already know. Okay, GS by 1 plus GSHS for the negative feedback. Okay, so this is closed loop transfer function for the negative feedback. Okay, yeah, so if you see the sign here, okay, this sign, so this is negative feedback. Okay, and again if you see what is the for the positive feedback, the only difference will be you just replace plus with minus. Okay, so this is the only difference. Okay, so you know the poles of closed loop transfer function are called closed loop poles and zeros. Okay, and very important thing here, this one, 1 plus GSHS equal to 0. So this is called characteristic equation of the transfer function. Okay, closed loop transfer function. So this is very important because we have to find out the poles of the closed loop transfer function. Okay, so this is called as characteristic equation. Okay, so this term will be very important in our further lectures. Okay, okay, so you see they have derived the for the positive feedback, this is the transfer function. Okay, I think up to here, okay, this is all. Okay, what is the open loop transfer function? Which is GS into HS. Okay, so how to get this? We have to just in the lecture also it's given that we just cut from here. Okay, the red one. Okay, just you cut the closed loop transfer function and you just derive it. You'll get GS into HS. So this is called as open loop transfer function. This is very important because in the question if they ask you what is open loop transfer function and if HS is not equal to 0, okay, HS is, so normally HS will be equal to 1, so it's called as unity feedback system. Okay, if HS is not equal to 1, then open loop transfer function is GS into HS. Okay, okay, so and we have seen performance specification. Okay, so how do we see performance specification? Okay, for the first order or second order we usually give the unit step response. Okay, so this is the transfer function for first order, so you don't have to remember it, you know how it is first order, just see the transfer function. Okay, 1 by TS plus 1. Okay, first order, directly you can see it has one pole. Okay, so it's stable because it is lying in the left hand plane, right, and it has zeros are none. Okay, so basically we have derived its response for various inputs. Okay, but we are mostly interested into this unit step response. Okay, because we want to find out different parameters of this response, right? So one is called time constant, right? So what is time constant? Time at which the output magnitude is 63.2% of its final value. Okay, so here the final value is equal to 1, but it can be anything. Okay, So this is the time constant. Within one time constant, your output magnitude is 63.2%. Okay. So and what is 40? 40 is the settling time. Okay. So time taken for the output magnitude to settle within 2% of its final value. Okay. So 2% is very small error. So we say it has already gone to its final value. Okay. So that's why we take 40 as the settling time. Okay. Settling time is where your system is settled. Okay. So this is your output, right? Response of the system. And we say, okay, it has settled to the final value. So that's why we are calling 4t or 4 tau as settling time. Okay. So, okay, unit step response. So you have seen other variants also. What do you mean by other variants where we have apart from t other variables? Okay. So in the first example, only t was the variable. Here input is scaled by b. Okay. So since it's a linear system, so output is also scaled by b. That is the only difference. Okay. If you see the output again, the output will be reaching b instead of 1. Okay, simple. Again, if we add a delay, then we'll say it's a, if you see this parameter model, and we have to use Paddy's first order approximation, right? And we have just seen the introduction of second order system. So we'll be doing in the week 4, second order system. So any doubt in the theory part, then I will go to the numericals. Any doubt? So it was very simple. Okay, just we have seen what is the effect of zero on the plant transfer function. Okay, and about the closed loop system. Okay. Okay, so let me do the numericals. Okay, I don't know you have done these numericals or not. Okay, can I get feedback from you? Like, have you done these numericals? So these are like previous semesters questions. Okay, for the NPTEL batch. Because I'm going to repeat 15 questions here total. Okay. So let me start. Okay, so I'll read the question and you just try to see the steps, and also you can do your own calculation also. Okay, because it's totally related to finding out the transfer function poles and zeros and the response, right? So already in the week 2 also, in week 1 also, we have seen how to do the Laplace transform and find out y of t, okay, and the steady state value. Similar questions. Okay. So first question I will read. The LTI system is governed by this equation. The dominant pole is, okay. So you have to find out the dominant pole. So first is I told, like, you see which pole is nearer to the origin. Okay. Then you can find out, or also by looking at the output also. Okay. So we have to find out y of t. So let me first write out this. Okay. Let me take some other. Okay. So this is the equation that is given to us. Okay. So let's apply the Laplace transform. Okay. Okay. So while applying Laplace transform, I'll just assume all the initial condition to be 0 to get the transfer function, right? So I'll not write y of 0 terms. Okay. So this is y square y of s. Okay. Just taking y of s common. So it's s squared plus 12s plus 20 equal to u of s equal to s plus 4. Okay. So what is the plant transfer function? Y of s by u of s. We call it p of s. Okay. So initial condition equal to 0. So s plus 4 s square plus 12s plus 20. Okay, so can you find out the poles of this transfer function? Okay, so this is your numerator function and this is denominator function. So how to find the poles? We put ds equal to 0, right? So ds is equal to s square plus 12s plus 20 equal to 0. Okay, can you tell me the poles? Okay, can I write this as 2s plus 10s plus 20 equal to 0? Okay, s plus 2, s plus 2, this is s plus 10 equal to 0. So roots are s plus 2 and s plus 10. Okay, so roots of ds are is equal to minus 2 and is equal to minus 10. Okay, these are the roots of ds and these are also poles of transfer function. Okay, okay, so let me plot this in complex plane. Okay, so this is imaginary and this is real. Okay, so minus 2 is here. Okay, this is minus 10. Okay, so just by looking at this transfer function, can you tell me which is dominant pole? And this is origin. So out of minus 2 and minus 10, okay, which is dominant pole? Do I need to find y of t? Okay, you can answer. Okay, what do you think? Do y of t directly in this S plane? Okay, we can directly say which one is the dominant pole. Okay, okay. So to confirm, okay, what I told you, okay, the pole which is lying nearer to the origin. Okay, that's called as dominant pole. Okay, directly I am specifying that this is the dominant pole. Okay, because what you will get, okay, you'll get something a s plus 2 plus b s plus 10, right? You'll get this response. Okay. So if you take inverse Laplace, you'll get a minus 2 by t plus b e minus 10 by t. Okay, this will be the response. Okay, so you have to see which one is greater, a or b. Okay, then only you will find out what is the response. Okay, and also if you see its graph, so if I don't know what is a and b, so it should be and let's assume that, okay, let me just sum this a and b. Let's say a and b are both equal to 1. Okay, okay. So I'm just drawing the response of e of minus 2 and e of b. Okay, so let's say both the coefficients are equal to 1, a. Okay, so let's solve it, a. So what will happen? Okay, so this for e of minus 2t. Okay, in the okay, this will be the response of e of minus 2t, 10t, right? So this will be the response, right? This will be the response. So E of minus 10t so this 10t coefficient at the time so E of E raised to minus 10t faster. Okay, so if you try to find out the coefficient, okay, here A and B are different. Let me just write what are the coefficients. So if you try to find what is A, okay, so directly put S equal to minus 2. So the denominator will be equal to 2 and 2 by, if you put that 2 by 8. So let me find out what is B. Okay, we'll put minus 10. This will be minus 6. Okay, and this is minus 8. 18. I hope this is correct. Coefficients A and B. Directly I have written it, okay? Because you know how to do that, okay? So you know this is greater, right? 2 by 8 is greater than 6 by 8. Okay, so actual response will be like this. Okay, so just this and just replace with this values. Okay, this is 2 by 8 and this is 6 by 8 if I am right. Okay, and this is E of minus 2t. Okay, so this is the response. So this is y of t. Okay, just by seeing this you can tell. Okay, so which will dominate, because y of t is summation of both this. Okay, summation of blue and the red one, but this is the dominant one, right? You can see from the response itself. Okay, so this is the dominant one. Dominant. Okay, and also I told you which is nearer to origin, so that's called as dominant pole, right? Because of this, so we have seen the effect also, right? Whichever pole which is nearer to the origin is dominant pole. Okay, and how to confirm that? By seeing the response y of t. Okay, you can confirm it is the dominant pole, right? So any question in this? Any doubt you have for this particular question, first question? Okay, so the answer is this one, is equal to minus 2. Okay, so first what I have done, equation was given to me. We took the Laplace transform. Okay, so Laplace transform. So after that we found out the transfer function. Okay, s equal to minus 2 and s equal to minus 10 are the two poles, and s equal to minus 2 is nearer to the origin. Okay, so that's why I'm saying it is dominant pole. Okay, and to confirm, we have also found out y of t. Okay, and y of t, if you see the coefficients a and b, a is coming out to be 2 by 8 and b is coming out to be 6 by 8 if my calculations are correct. Okay, and if you plot this response y of t, you can see here the red one, the red response is dominating. Okay, any doubt? Okay, you can write in the chat box also. Okay, if you have any doubt. Okay, I'll go to the next question. So the steady state value of the unit step response of the system given in problem one is, you have to find the steady state value. Okay, let me write the transfer function. P is equal to y of s by u of s equal to s plus 4, s plus 2 into s plus 10. Okay, so this one. So this is the plant transfer function. Okay, so I've written s plus 4 by s plus 2 plus s plus 10. And you know, since both the poles are lying in the left hand plane, okay, so we can say this system is stable, right? For y of s, Y of s is what? Y of s in the question, it's given as step, unit step, right? Okay. So unit step. Okay. So Y of s is equal to 1 by s, and for 1 by s, this will be stable, Bebo stable. Okay, from the week 2. Okay, so we have to find out steady state value. Okay, so what do you mean by steady state value? Limit t tend to infinity, y of t you have to find out. Okay, so what we can do, we have learned a very important theorem, right? So that is called as final value theorem. Okay, so to find out the steady state value, we can apply final value theorem. So what is that final value theorem? Limit s tends to 0, s into y of s. Okay, so you'll get the value which will be equal to this. So this is steady state value. So one thing is you can, so this is the transfer function, right? You can find out y of t and you put limit t tend to infinity and find out the steady state value, or you can use the final value theorem. Okay, so let me use the final value theorem here. Okay, so I'll write out using final value theorem. Okay, s into y of s is what? S plus 4 into s plus 2 into s plus 10. Okay, so into u of s, u of s is given as this, right? 1 by s, you know, this is unit step. Okay, unit step is the input, and the Laplace transform of unit step is 1 by s. Okay, so just put the limit 4 2 into 10. So 4 by 20, right? Okay, so this is the steady state value. So any doubt? Steady state value of the unit step response is 0.2. Okay, you can find the y of t also. Okay, so but you have to find the y of t. First you have to find this y of s is equal to this s plus 4 into s plus 2 into s plus 10. Okay, this. Okay, just find the y of t. Okay, you'll get something 1 minus a e minus 2t. Okay, minus b e of minus 10t. You'll get the response like this. So, and this one, sorry, a b, and let me call this coefficient as, okay, let's call this c. Okay, so this is the steady state response. Steady state response. Okay, when t equal to infinity, what will happen? Only c will remain, right? So in the previous question, this is not y of t. Okay, so this was wrong. This is not y of t, right? I am not calculated this y of e minus 2 sorry, a. So let me just form. So y of t will be something like that: a minus e minus 2t minus b minus 3t. Okay, so this will be the response. Okay, so I have not taken this c. Okay, I'm just comparing a and b value. Okay, just comparing a and b value. That's why I have drawn this. Okay, this is not response. Okay, so this is how you calculate. If you want to find out y of t, then you put limit t tend to infinity, and these two terms will become 0. Okay, so you'll be getting only y of t tend to infinity only c. Okay, then c will be equal to 0.2. Okay, so this is the right answer. Okay, any doubt in this question? Again, very simple. Using final value theorem, you can get the answer. Okay, so let's go to the next question. In the unit step response of the system given in problem 1, the coefficient that multiplies the exponential term whose exponent is the dominant pole. Okay, so from the first question we know dominant pole is equal to -2. Okay, and we have to find out the coefficient that multiplies the exponential term. Okay, so now what we have to find out, so this will be the response. Sorry, let me just add plus. Okay, so this will be the response, and we have to find out what the coefficient that multiplies the exponential term whose exponent is dominant pole. So we have to find out a. Okay, because s equal to -2 is the dominant pole. Okay, so for this we have to find out y of t. Okay, so you see y of s is known. So let me just find out. So y of s is known as plus 4 plus 2 and s plus 10. Okay, and y of s is, so this is ps. Okay, s plus 4, s plus 2, s plus 10. Okay, if you multiply u of s, okay, so I'm directly writing here 1 by s. Okay, is equal to s plus 4 s into s plus 2 into s plus 10. Okay, so which will be a by, okay, let me say this is, let me call this as c by s plus a by s plus 2 and b by s plus 10. So let's find out the coefficient here. So how to find s coefficient? Okay, so let me call this as equation 1, right? So what do you do to find out the c? So multiply by s. Okay, multiply by s and put s equal to 0. So what you will get? Okay, let me write c. So it will be 4 by 2 into 10. Okay, this is 2 by 10. You get 2 by 10, which is 0.2, and that was also steady state value. Okay, already calculated in the previous question. Okay, we can confirm from here also. So what is the coefficient for a? That's what is asked in the question. Okay, so what you do, you multiply s plus 2, okay, in equation 1, because equation 1 is equal to this, right? So you just multiply right hand side and left hand side by s plus 2. Okay, so what, and put s equal to -2. So what you'll get, just directly writing. Okay, so this will be -2 plus 10. So this will be 2. Okay, -2 into 8. So -1 by 8, if I'm correct. Okay, so, so any doubt how I got this a coefficient a? Okay, because you know is, let me write this, is plus 2 s plus 10 is equal to c by s plus a by s plus 2, okay, plus b by s plus 10. So what I'm doing, multiply by s plus 2. Okay, if you multiply s plus 2, what you'll get, in the left hand side we'll get s into s plus 10. Okay, here we'll get c into s plus 2 by s plus a plus b s plus 2 into s plus 10. Okay, then what you can do, put s equal to minus 2. Okay, if you put s equal to minus 2, here will be minus 2 plus 10. Okay, see, this term will be 0. Okay, 0 plus a plus again this will be also 0. Okay, so that's what I have done here. Okay, so a will be equal to 2 by minus 2 into 8. Okay, so 2 gets cancelled, so it becomes minus 1 by 8. So a is equal to minus 1 by 8. So what is this? Minus 1 by 8. Okay, 1 by 4 is 0.25. If we divide by 2, it is minus 0.125. Okay, so this will be 125. Okay, so let me also calculate this. B also. Okay, so to find B, so I'm directly writing it. Okay, again same thing you have to do, just multiply equation 1 with s plus 10. Okay, so you'll get B, so it will be minus 10 plus 4 minus 10 minus 10 plus 2. Okay, here minus 6 minus 10 into 8. Okay, like 6. Okay, I'm just writing and not factorizing it. 6 by 80. So let me write the output response equation. So y of t, so c is 0.2. Okay, so a was equal to minus 1 to 5 e of minus 2, and this last part b is equal to plus 6 by 80 e of minus 10t. Okay, so this is not asked. Okay, so this is steady state. Okay, steady state value. Okay, so what is asked in the question? The coefficient that multiplies the exponential term whose exponent is the dominant pole. Okay, so you have to find out this. Okay, so that is the correct answer. Okay, so any doubt you have in this question? Again, very simple question. Okay, so you have to find out this. You have to find out y of t, and they are asking you the coefficient for e of minus 2t. Okay, simple. Okay, let me go to the next question then. Zero of transfer function in the right half complex plane is called. Okay, so if you see the transfer function will have something like, oh, let me give you an example. Okay, so right half plane. Okay, a zero of the a transfer function in right half plane. So I can say this one. Okay, so you can say it is s plus 2 and s plus 10. I don't care. So this, you see, 0 is in right half plane of complex plane. Okay, so you have seen this. So what this is called? A non-minimum phase zero. Okay, so we have seen its effect also. Okay, so it will not make the system unstable. Okay, but temporarily your response will be moving in the opposite direction. Okay, and this is called a non-minimum phase zero. Okay, so in the theory classes we have seen this. Zero transfer function in the right half complex plane is called a non-minimum phase zero. Okay, So going to the next question. The governing equation of first order LTI system with time delay is given. Okay, the approximate transfer function of this system using first order Pade approximation is. Okay, so it is like E of minus Ts. Okay, so what they are replacing with 2 minus S into Ts. Okay, and 2 plus S into Ts. Okay, that's what we'll do. We'll replace this delay term with this. Okay, so let me first write the equation. We have to find out the transfer function. Okay, y dot plus 2y equal to u. Input is delayed by minus 0.2 seconds. Okay, so let's find the Laplace transform for this. So initial conditions will be equal to 0. Okay, so y of s by u of s will be equal to e 0.2 s, so it will be s plus 2, right? And using Pare's approximation. Okay, so this is the approximation. Okay, so I'll write 1 plus s plus 2. So I'm writing it here. I'm just replacing with the approximation, right? So it will be 2 minus, okay, so minus 2 2 plus 0.2s, right? See, so okay, I'll not confuse this. Okay, let me just write minus t into s. Okay, so this will be st 2 plus st. Okay, so e raised to power minus ts. So here the t is equal to 0.2, right? So you see, this is the approximation. So this is Pade approximation. Okay. Okay, so the t is, so in our question t is equal to 0.2. Okay, so this is the transfer function. Okay, so let me just write the approximation. So this is 2 minus 0.2 s by 2 plus 0.2 s plus 2. Okay, you'll see which. Okay, so what you can do here, 2 gets cancelled, so above is 1 minus 0.1 s, this is 1 plus 0.1 s into s plus 2. Okay, so if you multiply 10, what you'll get? 10 minus 1 s. Okay, let me write 1 s as s by 10 plus s into s plus 2. So this is the approximate transfer function ps. Okay, so let us see which option is correct. You can see this one, right? Third, this option. So just, okay, 10 minus s, 10 plus s, and s plus 2. Okay, because we have a pole here. Okay, so this is the correct answer. Okay, so any doubt in this question? Very simple. You have to find out the transfer function and you have to account the delay. So to find out the transfer function, because of the delay, we use Pare's approximation. Okay, so it is given here, and the solution to this problem is this. So any doubt? Okay, so then we'll move to the next question. Okay, consider a negative unity feedback system whose plant transfer function is given, okay, and controller transfer function is s plus 1. Then the closed loop transfer function is, so you've seen closed loop transfer function, okay, which is equal to gs by 1 plus gs into hs. Okay, so let me just draw this. Okay. And this is hs in the feedback path. Okay, and so this is the forward path, right? This is the forward gain. Okay, so in the forward path, what we have controller in it and the plant. Okay, so we have seen gs is equal to, okay, so gs is equal to c of s into p of s, right? So what I can do, I just can replace this with cs and ps. Okay, ps is the plant transfer function and cs is the controller transfer function. Okay, so I've written gs equal to cs into ps. Okay, so then the closed loop transfer function. Okay, so what is given? This is p of s is given and the controller transfer function. Okay, c of s is given. Okay, and negative unity feedback. So what does it mean? Unity feedback is h is equal to 1, right? So this is h is equal to 1 and we have to find out the closed loop transfer function. Okay, so it will be equal to cs hs equal to 1, so I'm not, okay, let me write here hs 1 plus cs, okay, 1 second, so it will be cs into ps, okay, into ps into hs, okay, and hs is equal to 1, so that's why I'm just not writing, it is equal to 1. Okay, so you have to find out cs into ps divided by 1 plus cs into ps. Okay, so let's first find out g of s, which is cs into ps. Okay, so cs is given in the question 5 by s square minus 2s, and sorry, this is not, so let me write this way, cs into ps, cs is given as s plus 1, ps is given as 5 by s square minus 2s. Okay, I think, yeah, 5 by s square minus 2s, and this is equal to 5 by s plus 1. Okay, so this is gs. Okay, and you put this in this. Okay, I see one comment. Okay, once again, tell me 3 and 4th answer. So you want to see only answer. Okay, let me first do this question. Okay, after that I will show you. So this is gs. Okay, so you have to put this in this. So let me call this equation 1. Okay, equation 2. So we'll put gs in equation 2, which will be closed loop transfer function. Okay, this is 5 into s plus 1, s into s minus 2. Okay, 1 plus 5 s plus 1 s into s minus 2. Okay, So let me again, this is GS, this is again GS. Okay, HS is equal to 1. That is given in the question. Okay, so if you simplify this, we get this s minus 2 plus 5 into s plus 1. Okay, this is s square minus 2s plus 5s plus 5. Okay, so this is equal to plus 3s. Okay, 5 into s plus 1 by s square plus 3s plus 5. Okay, so this is the closed loop transfer function. So let's see in which form it is given. Okay, so yeah, final answer is 5 into s plus 1 s square plus 3s by 5, s square plus 3s plus 5. Okay, so this you can see 5 into s plus 1 by s square plus 3s plus 5. Okay, so this is the correct option. Okay, so CS and PS was given, we have to find GS and just here this equation 2, which is GS by 1 plus GS into HS. So HS is equal to 1, so that's already given in the question because they said it's a negative unity feedback. Okay, that's why HS is equal to 1. Okay, so just by putting GS here, we get to this closed loop transfer function. Okay, so any doubt in this question? Okay, so I got one comment. Fourth, third and fourth answer. Okay, third and fourth. So this is third one. Okay, the unit step response of the system. Okay, so I'll start from here. Okay, so you got this PS equal to y of s by u of s equal to this. Okay, so let me shape this. So you got this. Once you got this, you can find out y of t, right? So unit step response of the system, and we have to find out the coefficient that multiplies the exponential term whose exponent is the dominant pole. Okay, whose exponent, what is exponent? E of, this is the exponent, right? These are the exponent terms. So in y of t, e of minus 2t and e raised to power minus 10t are the exponent terms. Okay, and we have to find coefficient that multiplies the exponential term whose exponent is dominant pole. Okay, whose exponent is dominant pole? This one. Okay, so these are two exponent pole, and this is the exponent of dominant pole. Okay, so in the question one, we have found out s equal to minus 2 as the dominant pole, and what is the exponent of that? E raised to power minus 2t. And in this question, we have to find out the coefficient of that. So the coefficient of that is equal to a. Okay, to find out a, we have found out the response. Okay, so this is how you typically find out the coefficients. Okay, by keeping a, b, c, and then you multiply. Okay, so to find out a, what I did, so this is equation 1, just multiply right hand side and left hand side. So this is the equation 1. Okay, so this is equation 1, so I have written. Okay, so this is your left hand side and this is your right hand side. Okay, so simply you multiply s plus 2. Okay, so you'll get this and put s equal to minus 2. And if you put s equal to minus 2, you'll get the coefficient of a, so which is coming out to be minus 1 by 8, which is equal to minus 0.125. Okay, so that's what it is asked. Okay, so the exponent of dominant pole, so minus 2 was the dominant pole, is e raised per minus 2t and its coefficient is a. That's what you have to find out. And in question number 4, okay, a zero of transfer function in the right half complex plane is called, so it's a theory question. Okay, so it's a non-minimum phase zero. Okay, because of pole present in right hand side. So any doubt in this? Simple questions. Okay, so just now we have done question number 6. Okay, okay, you can ask doubt anytime you have. Okay, let me do question number 7. If one consider unity positive feedback in problem 6 with everything else remaining the same, the corresponding closed loop transfer function is. Okay, so again, just focus on this point. Now it is positive feedback. Okay, so closed loop transfer function for positive feedback is equal to, gs by 1 minus gs hs. Okay, and for the unity feedback you can directly say it is hs is equal to 1. Okay, so I'm writing gs by 1 minus 1, gs by 1 minus gs. Okay, so in the previous question we have found out gs by 1 plus gs. Okay, so only difference is that. So let's quickly find out. So gs, what is the gs was 5 into s plus 1, 5 into s plus 1 s square minus 2s divided by 1 minus 5 s plus 1 s square minus 2s. Okay, let me just, so you have to find out this. So this is gs. Okay, which will be equal to 5 into s plus 1, okay, s minus 2s minus 5s minus 5. Okay, so this will be equal to minus 7s. Okay, so this is closed loop transfer function for positive feedback. Okay, s square minus 7s plus 5. So the first option you see 5 into s plus 1 divided by s square minus 7s minus 5 is the correct answer for this. So any doubt? So only a difference from the previous question is here in the denominator instead of 1 plus gs we are putting 1 minus gs and we are calculating the value. Okay, so only denominator is changing. Very simple because of positive feedback system. Okay, quickly we'll go to the next. Okay, which one of the following statement is true about problem 6 and 7? Okay, 6 was about negative feedback. Okay, and 7 was about positive feedback. Okay, the closed loop system is stable with negative feedback but not with positive feedback. Okay, so let's see the transfer function. Okay, so this is the transfer function. Okay, so you can see here, if you find out the roots also. Okay, so you see closed loop, if you want to find out the closed loop poles, what you do, s square plus, okay, me let me write this to transfer function here and then you can see. So for the question 6, okay, closed loop transfer function is equal to 5 into s plus 1, okay, this is s square plus 3s plus 5. Okay, again for 7 question we have closed loop transfer function as 5 into s plus 1. Okay, s square minus 7s minus 5. Okay, so these are the two transfer function. Okay, let me check 3s plus 4. Okay, so you have to find out the closed loop. First statement says for the closed loop system is stable with negative feedback but not with positive feedback. So you have to find out this is stable or not. Okay, okay, so let's how to find the roots for this, because we have to find out whether the system is stable or not, we have to find out roots of the denominator. Okay, we have to find out the poles, and we have to find out if poles are lying on the left hand side or the right hand side. If they are lying on the right hand side, we'll say the system is unstable. Okay, so for that what we have to find out, we have to find out the roots for this. Square plus 3s plus 5 equal to 0. Okay, let me find out the root by using the formula. Okay. So this is quadratic formula. Okay, so 4 5 4 into 5 is 20. Okay, this is some minus 11. Okay, this is 2, so the roots will be imaginary. Okay, so I'm writing this is J11. Okay, let me, okay, so you can see here this term, okay, so it is negative real part. Okay, so let me just draw where the roots, where the poles will be, somewhere here. Okay, so okay, this will be minus 3 and this will be 11. Okay, this is imaginary, so this is 3 and this is real. Okay, so what you see. Okay, so our pole should not lie in this region, right? So that's what we have to check for the stability. Okay, and it is not lying in that region. Okay, it's lying in the left hand plane. Okay, so what we can say, therefore the system is stable. Okay, so the same thing we have to confirm for the positive feedback. Okay, so this up to this is true, closed loop system is stable with negative feedback. Okay, let's check with the positive feedback. Same thing we'll do for this also. Okay, so s square minus 7s minus 5 equal to 0. We have to find out the poles. Okay, 7 plus minus b square is 49 minus, so what is this, 49 into 4 plus, sorry, just, okay, this is s is plus 7 square minus 4, this is minus 5. Okay, 2 into 1, simple. So this will be 7, and if you see 49 plus 20 by 2 into 1. Okay, so one root will be plus 49 plus 20 is how much, 69. Okay, so this is one root and this is the other root, minus 69. Okay, and this is positive, right? This will be positive. So let me write with other So this will be positive, but if you see 7 minus root of 69, okay, because root of 49 will be 7 and root of 69, so root of 69 will be greater than 7, right? Because of that, this term will be negative, okay? So if you plot this in complex plane, okay, so one root will be here, okay, this is 7 plus 69 by 2. Okay, sorry, I've done a mistake here. Okay, so okay, so this will be positive, negative. Okay, so it will be 7 minus 49, and this will be 7 plus 49 by 2, right? This is s equal to, right? So what is happening? You see here, okay? So one pole of closed loop transfer function for the positive feedback is lying in the right half plane. Okay, so what we can say about the transfer function, okay, or the system, we can say the system is unstable. Okay, because of the pole. Okay, so this is pole in right hand side. Okay, because of this our system is unstable. Okay, so the first statement says closed loop system is stable with negative feedback but not with positive feedback. Okay, so this statement is correct, right? So we have just confirmed also by finding out the poles, whether they are lying in the right hand plane or the left hand plane. Okay, 69 in model graph. Okay, I got this. Sorry, thank you for correcting. Okay, so this is not 49, so this is like 7 minus root of 69 by 2. Okay, so this is 69. Okay, okay. So this is correct. Thank you. Okay, so first statement is correct. Okay, so let's see the second statement. So it's the closed loop system is stable with positive feedback, but not with negative feedback. So this is incorrect. Okay, a closed loop system is stable with both positive and negative feedback. This is also incorrect. The closed loop system is unstable with. Okay, this is also incorrect. So only statement, first statement is correct. Okay, already verified. Okay, any doubt in this question? Question number 8. Okay, so by finding out the poles of closed loop transfer function, we are able to find out whether the system is stable or not. Okay, okay, we'll go to the next question. Okay, so the open loop transfer function corresponding to problem 6 is, okay, first let me define what is open loop transfer function. Is equal to, GS into HS. Okay, and so in question 6, in all the question, HS is equal to 1. Okay, and this GS is equal to CS into PS. Okay, CS is controller transfer function and P of S is plant transfer function. So let's go to the question number 6 and find out what is its CS and PS. Okay, this is question number 6. Okay, okay, so CS was equal to S plus 1 and S plus 1 or S plus, okay, we'll check it once again. This 5 by S square minus 2S. Okay, let me again check. it is 5 by s square minus 2s and s plus 1. Okay, so let's find the open loop transfer function. Plus 1 into 5 into s square minus 2s, which is equal to 5 into s plus 1 s square minus 2s. Okay. So this is the correct answer. So 5 into s plus 1. Okay, this one, last one. 5 into s plus 1 by s square minus 2s. Okay, I think very simple question here. Okay. We'll go to the 10th question. The open loop transfer function corresponding to problem 7. Again, this is also very simple. Okay, so open loop transfer function for the positive feedback system. Okay, we're just cutting down the closed loop. So again, that will be same, right? Whatever the case, positive or the negative feedback. Okay, so open loop transfer function is GS into HS, and you know HS is equal to 1. Okay, and this is what CS into PS. Again, same repetition of the previous question. Okay, so both the open loop transfer function for positive as well as negative feedback will be same, exactly same. Okay, so here your option will be right. Okay, I will write here open loop transfer function for negative feedback. Okay, if P is the feedback is equal to open loop transfer function. Okay, for positive feedback. Okay, both are equal and both are equal to GS into HS. Okay, that's why they are equal. Okay, any doubt in this question? Same. Okay, we'll go to the next question. Okay, 11th question. Which one of the following statement is true about a stable first order LTI system? Okay, so let me write the transfer function here, which is equal to what? 1 by Ts plus 1. This is the simplest transfer function. Okay, so the unit step response always converges to 0 as time increases to infinity. Okay, let me write. So this is equal to ys by us. Okay, so already that is whatever this question is asking is already covered in the lectures. Okay, I'll just show you. Let's discuss once again. Okay, so it will be equal to, let's call this as PS, plant transfer function, PS into US. Okay, so u of s is equal to, because in the first statement unit step we have to find out. Okay, so ts plus 1 into 1 by s. Okay, again you know how to calculate y of s. This will be a by s plus b by ts plus 1. Okay, again to calculate a, what you do? Okay, again multiply left hand side by s. Okay, because when I say left hand side, right hand side, you're writing this as s plus a by s plus b by ts plus 1. Okay, that's what I'm saying. So this is left hand side and this is right hand side. That's what I'm saying. Okay, multiply both the sides by s and then put s equal to 0. Okay, so if you put s equal to 0, what you will get? A is equal to 1. Simple. Similarly, do the same thing with the b. Okay, just multiply both the side by ts plus 1 and put s equal to what? Minus 1 by t. Okay, so if you put, that will be what you will get, minus t you will get. Okay, this will be ts plus 1. Okay, y of s. Simple. So inverse Laplace transform is this 1 minus t into, Okay, let's first convert in this in our form. Okay, so let's first convert as, so this is t. If I take t common, it will be s plus 1 by t, right? And this gets cancelled, so 1 by s minus 1 by s plus t. Okay, so if you take the Laplace transform, you'll get 1 minus e raised to 1 minus, okay, let me, okay. So this is 1 by t. Okay. So t by t you will get. Okay, so this is the final response. So how the final response will look like? Okay, let me draw with the red pen. For unit step, this is 1. So I'm finding y of t with respect to time. So your response will be looking like this. Okay, that we have seen already in the lecture. At t equal to infinity, it will go to steady state value of 1. Okay, so the first statement, what it says, the unit step response always converges to 0 at time increases to infinity. Okay, this statement is wrong, right? You see, as t tends to infinity, it converges to, so from mathematics also you can see, as t tend to infinity, y of t, if you are able to find out from the figure itself, from the its graph itself with respect to time, you can find out that t equal to infinity, y of t will become 1. Okay, so here also you can put the limit and you'll find out that it will be equal to 1. Okay, so this statement is wrong. The unit impulse response converges asymptotically to a non-zero value as time increases to infinity. Okay, so here we have found out the unit step response. Okay, so what will happen for the unit impulse response? So here y of s will be equal to 1, you know. Okay, the Laplace transform of unit impulse is equal to 1. Okay, so what you will get, y of s will be equal to 1 by ts plus 1 into 1. Okay, directly you can find out the inverse Laplace transform. Okay, so y of t will be equal to how much? So if I take 1 by t outside, okay, so it will be e minus t by t. Okay, so how the response will be? So let's focus on the response part. Okay, at t equal to infinity, the response will be like this. Okay, so your response, so this is y of t at b. Okay, so just focus on this part. As t tends to infinity, y of t will be going to 0. Okay, so what does the second statement say? The impulse response converges asymptotically to a non-zero value. No, it converges asymptotically to a zero value as time increases to infinity. So this statement is also wrong. Okay, so we have seen here. Okay, third statement is the magnitude of unit ramp response tends asymptotically to a finite value as time increases to infinity. So I'm not going to do a proof for this. Okay, so because you know the response will be looking like this. So let me show you the uh, ramp response. Okay, so u of s is what, 1 by s square. Okay, so you will get the response like this. So this is input. Okay, so let output will be something like, Just focus on this part. So I'll shade a different color. So this part, at t tends to infinity, what will happen to this output? Okay, this is the output. So it is also going to infinity, right? At t tends to infinity. Okay, you can refer to your lecture notes. So at tending to infinity, what is happening? The magnitude of unit ramp response tends asymptotically to a very large value or infinite value, okay, as time increases to infinity. So this statement is also incorrect. Okay, it goes to infinity. It's not to a finite value. Infinity is not a finite value. Okay, the last statement is it has one pole in the right half complex plane. Okay, so this statement is correct, right? You see this? So it has one pole here, minus 1 by t. Okay, so this is explained. Okay, so this statement is correct, right? It has one pole in the right half complex plane. Correct. So any doubt for this question, 11th question? Okay, so let's go to the next question. So at a time instant equal to thrice the time constant of a stable first order LTI system, the ratio of its unit step response value to the final asymptotic value of its unit step responses. So let's take this system. Okay, PS is equal to 1 by TS plus 1. Okay, T is what time constant, I'll write. You can write as tau also. Okay, so here it is T. So what you have to find out? Response. Okay, ES plus 1, and you have to find out, and here U of S is what? Unit step. Okay, so what is the unit step response Y of S? So directly I will write, because in the previous question already we have found out the unit step response, which will be which is equal to 1 minus E of minus T by capital T, right? So this is the response, right? So in this, you just focus on this. Okay, so I've already calculated this in the previous question. Okay, so what it is asking, at a time instant equal to thrice the time constant. The ratio, it is finding the ratio. Okay, so let's find out the ratio of response value to the final asymptotic value. Okay, so you have to find the ratio. So ratio is equal to, you have to find y at 3t and to the ratio of unit step response value of final asymptotic value to its, okay, at a time instant equal to time instant. Okay, final, here final asymptotic value will be how much? So you'll get at 4 tau, right? So this is with respect to 2% error. Okay, so this is like practical. Okay, but in theory, what will be the output, final output? Asymptotically it will reach 1, right? So just find out, you have to find out this 3t by let me just to be very specific, write down this t tend to infinity. We have to find out this. Okay, we have to find out this ratio. Okay, because we know the denominator, right? If you see this, at t tending to infinity, y of t will be what? Equal to 1, right? So you have to just find y of 3t. Okay, because this will be equal to 1. Just if you see the response also, y of t. Okay, as t tends to infinity, this e this term will become 0 and you will be left with only 1. Okay, so let's find out y of 3t. So how to find y of 3t? Just put in yt equation 1 minus e, so 3t by t. Okay, you see, so let's call this equation 3. Okay, so at t equal to 3t you have to find out the value of the response. Okay, so this you will get, so 1 minus e minus 3. Okay, so can you find out what is this value? 1 minus e raised to power minus 3t. Okay, it will be around 0.95, I think. What you're getting? So I'm not calculating it. Okay, it's very straightforward. To get the answer for this, you have to find out 1 minus e raised to power minus 3t minus 3. Okay, so I'll directly write the answer. I think it is 0.95. I don't know. Okay, you calculate it. Okay, okay. So very simple in this. Okay, response you know, and you have to find out the ratio between when the time instant is equal to thrice the time constant to when the response is to the final asymptotic value. Okay, final asymptotic value is given by this. Okay, but in practice what we take this value, right? 40, because at 40 we say it is almost reaching to its final value with 2% error, right? But okay, so next question. So we have 13, 14, 3 questions remaining. Okay, when a system whose transfer function is this is subjected to a unit step input, the difference between the output and the input asymptotically tends to. Okay, so we are given with the transfer function, this one. Okay, and us is given as step input. Okay, 1 by s. So you have to find out. Okay, this you know, this is first order system, right? So basically, so this is one, right? And your output will be like this. Okay, you'll have some error, the difference between output and input. So this difference you have to find out as t equal to infinity. Okay, let's find out. You know, y of s is equal to ps into u of s. P of s is s plus 2, 1 by s. Okay, so this is like a by s plus b by s plus 2. Okay, to find the coefficient of a, what you do, multiply both the side by s and put s equal to 0. So if you do that, you'll get 1 by 2. So by s, similarly for b, what you will get, minus 1 by 2 by s plus 2. I hope I am correct. Please check. Okay, so I'm getting this. So let's find the inverse Laplace. What we'll get, y of t as 1 by 2 minus, it's 1 by 2 e raised to power minus 2t. So let me take one. Okay, let's write this. Okay, so this is the response, unit step response. Okay, and what we have to find out the difference between output and input. Asymptotically means t tending to infinity. Okay, let's find out the response when t tends to infinity. So you put this, what you will get. Okay, the second term will be equal to 0 and you will be left with 1 by 2, right? Okay, so let me correct this graph here. Okay, graphically also you can see. So this is 1, this is the input, right? And it is reaching like this. Okay, at t tending, this is t. Okay, this is, so let me change the color. So this is 0.5. Okay, so at t tending to infinity, you have to find out this difference. Okay, so let me call delta. Okay, so what is that? 1 minus half, which is equal to 0.5, right? So difference you have to find out. Okay, you know the input is always equal to 1, right? So input is not changing. So how the input is u of s, let me draw here u of s. Okay, it is like this. At t equal to 0, 1. Okay, this is your u of t, step response. Okay, and what is the, okay, so I have drawn both the response in this. So let me draw u of t here. So u of t is like this. So this is u of t. So this is equal to 1. Okay, t tending to infinity. So it remains at 1. Okay, and for response y of t, let me draw the response. So the response is like this. Okay, so it is only reaching 0.5 or half. Okay, as t 10. Okay, I'll not write t here. So this is t, right? So if you see at infinity point, what is happening? You'll get this graph, right? If you just superimpose both the graphs here. Okay, so you'll get this graph here. Okay, and you have to find out the difference, right? So difference at t equal to infinity is equal to 0.5 here, this difference. Okay, so difference between output. Okay, so output is equal to 0.5 and input is 1. So that's why this minus 0.5. Okay, this delta. Okay, so let me correct here. So they are asking output minus, so output is equal to how much? Half minus input. Okay, so which is minus 0.5. Okay, so any doubt in this question? 13th question. When the system whose transfer function is this is subjected to unit step input, the difference between output and the input asymptotically tends to. So basically, value like the input is not changing, correct? From t equal to 0 to t equal to infinity, it will remain constant, which is equal to 1. But if you see your output, okay, so your output is starting from t at t equal to 0. What is the output? Okay, equal to 0, right? At t equal to infinity, it will go and settle at half value. Okay, 1 by 2 value. So we have to find out the difference at that value. Okay, which is coming out to be minus 0.5. Okay, let's go to the next question. Okay, the governing equation of first order LTI system is given here. The steady state value of its unit step response. Okay, this is also very simple. Okay, for you, let's find the Laplace transform for this. Okay, 4 into u of s. So, okay, 4 by, this is u of s. Okay, 4 by s plus 2. and you have to find the unit step steady state value of unit step response. So this is equal to PS, right? So PS into UFS, okay, which is 4 into S plus 2. And what is U of S? Unit step. Okay, US is equal to 1 by S. Again, this find out this S plus 2 and same procedure I'm directly writing, okay? For S, it will be 2 by S, okay? For S plus 2, it will be minus 2 by S plus 2. Okay, please check. This is Y of t. Oh, sorry, this is not Y of t. This is Y of S. Again, we have to take the inverse Laplace transform to get the value. Okay, 2 minus 2 e raised to minus 2t. Again, what we can do, we can bring out the 2 here. So 1 minus e. So this is the value. Okay. I hope everything is correct. Okay, so this is the value, and what they are asking, the steady state value of unit step response. Okay, steady state value, what? Simple, t tending to infinity, you can put. What will it? Okay, if you see, this will go to 0 and you will be left with 2. Okay, so this is steady state value, right? So I think in this tutorial session itself, I think many times we have calculated this steady state value. Okay, so the answer is 2. Okay, so second is correct. Second option is correct. So any doubt in this? There shouldn't be any doubt because you are given with the equation, you take the Laplace transform, okay, and you find out what is Y of S, which is PS into U of S. U of S is given, that is given as unit step, right? And you just do calculate this many times you have done, okay, to calculate the steady state value. Okay, 15th, last question here, I think. Yeah. So the governing equation of first order system is given. Which one of the following statement about this system is true? I think first order system. Okay, this is different system. Okay, y plus 4y equal to u. Let's find out its transfer function by first finding out the Laplace transform. Find, okay. Y of s by u of s is equal to 1 by s plus 4. Okay, it has pole at s equal to minus 4. Okay, so you have to find out which of the following statement about the system is true. Its response as an oscillatory response. No. So you know directly by just seeing the first order transfer function, you can say, okay, for the unit step response, okay, for any type of response. Okay, the governing equation of first order LDA is again each one of the following statement. The response is oscillatory component. So you'll study in the next weeks. For the second order system, we have the oscillatory response. Okay, it does not have the oscillatory response for any type of input. Okay, so if you see different types of response, okay, for the impulse, you have seen this. Okay, there is no oscillatory, okay, oscillatory component, and for the unit step, what we have seen this type of response, right? So this is not oscillatory, right? And for the ramp also, that was not oscillatory. Okay, so you can say the first statement is wrong. Its response as oscillatory component. No, oscillations means if you're getting these type of response, then this is called oscillatory responses. Okay, that will see in second order system. But in the first order system, if you see the red waveform, you're not getting any oscillatory response, okay, for any input. So that's why its response is not oscillatory. Okay, so that's why the first option is incorrect. So it is unstable. So it is not unstable because you see it has pole at s equal to minus 4. Okay, let me change the color. Okay, so pole is equal to -4, okay, which is on left hand side of complex plane or S plane. Okay, so the system is stable. Okay, so this statement is also wrong. Its settling time is 1 second. Okay, its settling time is 1 second. So let's find out the response for this. So y of s is equal to what? S into s plus 4. Again, what you will get if you calculate this many times you are doing this. Okay, so this will be, okay, 1 by 4. You'll get this type of thing. Okay, so its settling time is 1 by s. So how in our lectures what we have defined a settling time as 4t, right, for 2% error. Okay, so this is the, okay, 4t. What is t here? So let me write the generalized response. Okay, we get something like this. So let's call it a coefficient 1 minus e minus t by tau. Okay, so this is the general unit step response for first order system. Okay, just so t by tau. Here tau is what? Just looking at this equation here, the tau is what? 1 by 4. Okay, just compare these two equations. Let me call this equation A and equation B. If you compare these two, you'll get tau is 1 by 4. So let's call it this. Okay, let me 4 tau. Okay, let me write this as 4 tau like this. Okay, settling time is 4 tau. So what is tau here? 4 into 1 by 4. Okay, tau is 1 by 4, right? So we are getting 1 second. Okay, so this is the settling time. Settling time for this system is 1 second. Okay, so this statement is correct. Settling time is 1 by state. Okay, just now we have found out. On last statement, what it says, the steady state value of its unit step response is 1 by s. So this statement is correct or not? So this is the unit step response. So let me just highlight this. So this is the unit step response we have calculated, and we know at steady state, at t equal to infinity, what is happening? You have to find out this. Okay, minus 4t. What you will do? This will be, the answer will be 1 by 4. Okay, because this term will be going to 0, right? So at steady state, value of its unit response is not equal to 1, right? It is equal to 1 by 4. See, so this statement is also wrong. This is also wrong. Okay, so any doubt in this question? So up to now we have done very simple question. Okay, so any doubt in the previous questions, whatever that are. So we have finished with all the questions. Okay, 15 questions. So any doubt you want to ask? With any of the questions that I've solved today? Okay, so I'll be uploading this session notes as well as this uh, video, whatever that we have done today, okay, by tonight. Okay, so if you have, okay, thank you. So thank you for attending the tutorial 3. So I'll see you on next Tuesday, okay, from 6 to 8. So we'll be covering questions based on week 4. Okay, so good night. Okay, someone has doubt. Vishwa and yes. Okay, Vishwa, you have any doubt? Okay, thank you for attending this session. So I'll end the session. So I'll, okay, okay, then it's fine. Okay, I'll meet you in the next session. Thank you.